So let's get started, everyone. So welcome back. So the weather's a bit nicer now than last week. So today we're going to be talking about hypothesis testing. So we started to talk about this on Thursday last week. We talked about a very specific example. Which was based on a discrete distribution. And so with that case, we could calculate the probabilities exactly. We could formulate the problem, some more precisely. Than last week. Let's see. So now we're going to talk about more generally. This more general version will mostly be looking at, again, we'll be relying on things like the central limit theorem, which means we'll be able to reduce the problem down to looking at the normal distribution or the t distribution. And so that's what we'll look at today. So hypothesis testing is probably one of the kind of most common things associated with using statistics. We'll get to things like the p-value at the end of the lecture today. And so it's to really understand this, it's going to build on kind of everything you've learned from probability up through the basic statistics up to this point. I will say these things are probably a bit less straightforward and direct than like the probability, calculations, and they're a bit trickier to understand and apply. I'll try not to rush through this. So if you look at the schedule, I've updated slightly a couple things on the schedule. So mostly, so what it says on here in the notes, I'll basically be going through the more kind of mathematical part of the lecture today with some examples, and then we'll go through stuff again in R and go a little bit deeper on this on Thursday. I will also try and kind of interject some commentary on how hypothesis testing is used and when it should be used, and when it's interesting to use and when not. Okay. So the other thing, to see in here is that like homework 6 is due today. Homework 6 was mostly on estimation and confidence intervals. We've heard that students found this homework a little bit more confusing. I think that's partially because this material is a little bit harder to wrap your head around. And partially, I think there's one question we intentionally tried to make a little bit tricky, and I think it was. But there was at least one typo on the homework as well. But if you answer it straight or how we intended, it should be fine. But if you have any questions on that, or if you haven't printed out a version of it yet, I've got copies up here, and I'll be available for questions after class. So we've been trying to estimate how many copies of the homework people will pick up in the lectures, and I have not been doing a very good job of that. Like the first time it was like 30 or so, then next time I printed 40, they all got taken. I think there were 53 that were taken, and then since then it's been like less than 20 every time. So yeah, so if you know what's going on, you can let me know. Maybe 25 people will pick them up after class today. So that'll be okay. So the rest of the semester after hypothesis testing is a bit more flexible. I was thinking about on Tuesday next week talking about permutation testing, which is a part of statistics I like. I think it's very general, useful tool. And then I was going to cover like a little bit of linear regression and phrase it in the way kind of in terms of the things we've learned in this class. You may have heard about it or used it in other places before. So that was the plan, and also a lecture on a complete review for the semester. As the schedule worked out, kind of copied from like previous semesters. I have the review on the Thursday before the last day of class instead of on the actual last day of class. Does anyone have just do like a show of hands? The two options would be the review on the Thursday on 420 or on Tuesday 425. So who would like it on Thursday 420? A bit more time to review. Okay, and how about 425? Okay, I think pretty evenly split. Probably would not, pass a test for significance. So as we'll see, but I'll probably move it to 425, and then we can, cover that stuff and do the review on the last day. The final exam is Monday, May 1st. Again, these dates are set by the school, like years ahead of time, or as soon as the schedule of the class is out. There's a practice exam linked off there and solutions for that exam. That's an exam from probably 8 years ago, but the material hasn't changed too much. It was from a different professor from the EC department, but it should be fairly representative of what you should roughly expect on a final. I mean, there's other finals linked. You can follow that, and there's a link to a page with a couple of other finals on it. You get a sense of what it'll be like. Again, you'll have 2 hours. It's going to be in class. All right, so they'll probably, some people have asked me about calculators. I'll probably allow calculators, although I don't expect there to be challenging calculations you have to do, right? You might have, add like 0.3 and 0.2 together, right? Sort of stuff that I'm not sure it's going to be faster to do in a calculator. So stuff that I expect you should be able to just do the calculations in your head. So will you be able to use notes? My intention is that it will not be open book, but you will have some sort of cheat sheet you will be allowed to bring in. The form of that we're still working out. And if you notice on the practice exam, it sometimes would ask for something like the Z alpha value or the T alpha value that you might need. And it, on the exam, it like provided some possible values you might use, right? So those sort of things where you have to look something up in a table effectively, you're not going to have to memorize the table. Okay, so not worrying about, stuff like that. Yeah, it's a question. It'll kind of be in between the quizzes and the homeworks. There definitely stuff on the homeworks I asked you that I thought was kind of tricky. This was intentional. Since you're all at like a top university and challenging majors, I expect you to be able to solve tricky questions with time to think about them. On the final exam, my goal is not to trick you, but is more to ask straightforward sort of things. But it's going to look like the homeworks, right? It's going to look in this like format of the homeworks, and you'll have to write your answers on here. So in that sense, it's going to be like the homework. But the questions will be fairly straightforward. They probably won't be like multiple choice sort of questions that we sometimes have in the quizzes, but they should be things that if you understand what you're doing, you should be able to kind of work stuff out. You might be able to ask you a little bit more calculation on the final than on the quizzes, but it's kind of should be more straightforward. So calculation. We're not trying to challenge you on the final. We're trying to test the core knowledge that we've, covered over the semester, right? So somewhere in between those two, yeah. There are some forms formulas I will expect you to remember, right? You will be able to have a cheat sheet, which you will be able to make. You could write formulas on there. Okay, so you don't have to remember them if you remember to put them on your cheat sheet, but you might just remember them. There are certain formulas that you will be using enough if you continue on doing this that you should ultimately just remember, like things like Bayes' rule and like the central limit theorem and what a normal distribution looks like. Those are formulas that ultimately you should just remember and internalize, right? If you draw a blank on the final, you know, that sort of thing happens. That's why you're going to have a cheat sheet. Okay, so I want you to memorize these, but try to be kind of like realistic, right? I think memorization is kind of not always the right thing to do, especially when things like Wikipedia are, you know, are like so handy, right? But you're not going to have to just like recall the formula. You have to recall it and then use it in some way, right? And that's what we're learning in this course. Yes. Okay. Great. As it gets a little bit closer and we kind of have formulation, probably in the next week or so, I'll tell you specifically like what is the cheat sheet and you know some other stuff like that. And when this is kind of stuff is more finalized, I will post something on Canvas so that you can see it and it's written down so clearly. So okay, great. Let's get on to hypothesis testing. Yeah, so we talked a little bit. Yeah, so just to review, well, you know, so hypothesis, testing is kind of part of statistics. Okay, so when we think of statistics, we should be thinking about we have x1, x2, up to xn. These are IID from some unknown distribution. Okay, we're going to somehow be working with thinking about working with some observations, some data, but these are random variables, and we need to start with these. And we're going to kind of plan. We're going to ask some question about this, and we'd like to learn. And the goal is to kind of use x1 through xn to kind of study f theta, right? So there's some distribution that these are drawn from. Think of f theta as describing the natural world. We're making observations from it in some way. The observations are x1 through xn, or we're planning on making observations. And then we want to study something about f theta. What's different about what we've done before, right, up until the hypothesis testing, is that we're going to have hypotheses, right? So we're going to have hypotheses, and so these are going to be some sort of like some guesses about f theta, and there are going to be two hypotheses. The first one is going to be the null hypothesis. We'll call this H0. It's the null hypothesis. And this is going to be something so boring, or kind of like something like something like standard, right? So this was in the example with the tea tasting experiment. The null hypothesis was that the lady was just guessing, that there was nothing like interesting going on, right? So the boring hypothesis is like the H0 hypothesis. That's like the status quo, right? Sometimes this would be called, so status quo. This is kind of the accepted kind of so like view of the world. That's kind of like, you know, if we don't have any data, this is probably what we think of things, right? And so, but there are two hypotheses. Okay, and the other one is the alternative. So hypothesis, and this is often called H1. So the H1 hypothesis, and so this is like a new claim. All right, so this is like in the lady tasting tea experiment. The lady claims that she could tell if the milk was put in first or if the tea was put in first. This is somewhat unusual. It would be interesting if true, right? So this would be kind of something interesting if so true, okay? And so now we'd kind of like to say, does the data support, do the observations support the alternative hypothesis with the null hypothesis as like the fallback or the default, right? So we didn't have any data. I'd probably say probably the null hypothesis is the case. But maybe I can gather data and then I can say, well, I think the alternative hypothesis is something that is possibly true over the null hypothesis, right? So okay, the other kind of thing to like see here about these hypotheses is that the null hypothesis we have to specify. So we have to specify this one exactly. Okay, we're going to be kind of calculating probabilities based on the null hypothesis. The alternative hypothesis, we can kind of say, well, it's going to be something that's different in some way from the null hypothesis. Something like, I think that the lady is better at telling if the milk is first or the tea is first than random, but I didn't have to say exactly how much better. Okay, so I said there's some alternative to the null hypothesis. I think the alternative is kind of so I don't have to it gets the kind of the advantage that I don't have to fully specify it. So like at the beginning. Sometimes in the process of doing this, you will fully specify what it's going to be, but I think in everything we're going to talk about, where you do the hypothesis without fully specifying the alternative. So this one is not fully specified. So this would be like something like if this was, for instance, I think there's a particular value for the parameter, so theta, and the alternative hypothesis might be that the true value of theta is larger, than like theta 0. Okay, so for the null hypothesis, I have to say theta 0, some parameter, is the parameter which is generating the distribution, right? So that the lady was guessing the t at random, so it was like the probability of any t being kind of milk first or tea first was going to be 0.5. And this one says something, well, if it is milk first, then she's more likely to guess that milk is first, but I didn't have to say by how much. Okay, so this one does not have to be fully specified. Okay. And then if it is, if we do decide the alternative hypothesis is something we want to kind of like follow up on, that it is kind of supported by the data, then we could use an estimator from the data to estimate this. Okay, whereas the theta zero parameter, for instance, we typically would not want to estimate. That's something we gain. We have knowledge like from the world. So okay, so this is going to be related to statistics, but at this point, when I'm specifying the hypotheses, I've not looked at any data yet. Okay, so I've not yet looked at any data. I'm making hypotheses about the world. It could be that maybe there's some data from prior data that that I've made these things. Right, so I've made this, but not the data we're considering in this experiment, in the testing process. So okay, so the hypothesis testing is going to have 3 steps. So hypothesis testing, it's going to have 3 steps. So step 1 is going to be hypothesis formulation. Okay, so that is the null H0 and the alternative H1 hypotheses. We need to form these about the data, or we're going to inform these about the world. Okay. Step 2. So once I've formulated the hypotheses, then I need to design the experiment. All right. So this is where I design the experiment. I'm going to now think about random variables. Okay, so I'm going to collect some random variables, x1, x2, up to xn. These are going to be some sort of observations about the world. And I'm going to think about these and say, well, what would they have to look like for me to believe the alternative hypothesis instead of the null hypothesis? Okay, so we're going to kind of think about what would these have to be, and kind of actually say, well, if I'm going to be 95% confident in something, right, then I want to see some values that look like this. Okay, and I want to plan this out ahead of time. I don't want to kind of set the threshold of what I'm willing, how confident I want to be after I look at the data. I'm going to do this all before I look at the data. I want to think, okay, some part of this design experiment, not something we will talk so much about in this class, but it's deciding how large does this value n have to be, right? So if I look at how many data points do I have to select, am I going to have to select before I think this experiment might be useful? I don't want to go. It would be not great if I went and collected some data and afterwards I decided, yeah, I think this alternative hypothesis is looking kind of believable, but I'm not totally convinced. I would need, more data to actually convince myself. Sometimes you can figure out how large the sample has to be. This is important if your collecting data is very expensive. So if you're doing like a health-based, survey, and collecting data involves finding a patient, getting their consent to be part of an experiment, running some sort of lab study on them to collect the data, and then putting all this together. And if you want to make sure you're confident with your prediction, if the alternative hypothesis is how you think, you want to make sure you have enough data, and then you go to like a funding agency like the National Institutes of Health and say, I want to run this study. If the data comes back like I suspect it will, then I would be able to support the alternative hypothesis. And this is how many patients I'll need to study, right? So these are things you do before you before you look at the data. Okay, and then there's a third step, right? And okay, step 3 is when you actually run the experiment. Okay, when you actually run the experiment, then you collect data. These are the lowercase x1, x2 up to xn, and then you at this point you consider the H0 and the H1 hypotheses in the context of your experimental design. Okay, so these 3 steps and getting them in the right order is going to be important here. Okay, so in order to do this, I'm going to need to fill in some details about these these steps. We're going to find things like a test statistic, a test statistic, and a critical value, which are going to come in step 2. And then we're going to look at accepting or rejecting the alternative, or accepting the alternative hypotheses, or rejecting the null hypothesis. That'll be something we do in step 3. Okay, so I'll now go through some examples and kind of specify specifically these steps. Okay, so let's start with an example about height. Okay, so let's look at the heights of the populations in various states, and so I'm going to have an alternative hypothesis that Utah population is tall. Okay, so I kind of have a hypothesis in some way that the people who live in Utah are somehow tall. So how would I kind of turn this into a null hypothesis and a specific alternative hypothesis? Yeah. Yeah, great. So a good null hypothesis is that people of Utah are about the same height as everywhere else. Yeah, okay, right. So null hypothesis that Utah people are about everywhere else. They're not taller than everywhere else. So then I should amend my alternative hypothesis, say that Utah people are not just tall, but taller than average. Okay, so I don't just want to say they're tall, maybe they're but taller to some sort of average, right? So then the standard distribution, right? So okay, now I need to model this. This is good, we're going in the right direction. I need to model this as a probability distributions, right? I need to model these as as probability distributions. How would I do this? Yeah, okay, great. So I want to start looking at my null distribution, and I want to get the the average height. So you said the varying states, so maybe we'll pick the United States average, right? So to get the average height of the US, right? So if I want to look up what is the average height in the US, I did this before the lecture. I said the average height in the US is going to be about what I said. Well, I'm rounding a bit, but let's say it's 67 inches, okay? So the average height in the US is about 67 inches, okay? You know, so let's say we're actually thinking about, we're gonna do an experiment here on campus. So let's say the average height of people in college, right? So average height people in college across the US, and that's how I got 67. It might be a little bit lower, but older people tend to be shorter actually. Once you get older, you shrink a little bit, but two, the average height of population has been growing. So people are older, they were part of an older generation. So let's say 67 inches, just simple round number. Okay, but I need a probability distribution. How would I model this as a probability distribution? Okay. Yeah, so maybe I would say like this. I can look up this as well and say what is the standard deviation across the US. I'll say this is about 5 inches. Okay, the standard deviation is about 5 inches, right? And now, okay, good. Let's say this is all the data I have, right? How would I turn this into a probability distribution? Yeah. Yeah. Yep. Also, are we testing the null hypothesis based on data from the US? Yeah, so I'm I need to start someplace with like a some common knowledge. Okay, I'm not going to when I run my experiment, I'm going to gather new data. The experiment you run should be on data that has never been collected and analyzed before. Okay, and in principle, that's how it should work. But so if data has already been collected prior, I can use that to form my null hypothesis. Okay, and so that's kind of what I'm doing here. In order to have common sense or worldly knowledge hypothesis about something, there's usually some data involved in that, right? I'd like to think we're like a data-driven society in some senses for questions like this. So there's like, I looked up on Wikipedia, right, or on Google, and I got some numbers that look kind of like this. Okay, so probably that's from data, but it was from Google. That's something like common knowledge, right? So imagine maybe like ChatGPT. You ask, this question to ChatGPT. It, it gives you this answer. Where did ChatGPT get its answer from? It's not clear, okay? But it gave you this data. Maybe that counts as like a common knowledge. Now you might want to test against that knowledge. I don't believe ChatGPT, so I should go gather data to go, see if that's right. Okay, in this case, we're gathering data from across the whole US, and maybe there has never been data collected in like the state of Utah about this before, which is, is not true. If you look up, I think Utah is actually the second tallest state on average. So this is kind of a like a relevant question, I guess. So we somehow decided that this is our null hypothesis based on, or this is forming our null hypothesis based on common sense knowledge about the world, whether that's Google or ChatGPT or Wikipedia or some, there's some book in the doctor's office, right? Yeah, so that answer your question? Yeah. Yeah, you should not think about this as, so gathering the data, you should think about this as data that's already been gathered that may not be specific to your question, but is kind of close enough that I can use it as like a baseline, right? So say, the data across all the US is a good baseline, but I want to know about Utah, and maybe I don't have that data in, say, Utah, right? So I'd like to test that Utah might be taller than the other, the rest of the US. Okay, so I started with the population in Utah is tall, but to do a null kind of a hypothesis test, I have to compare it against something. And if I compared it against like the world population, that might be different than like the US population, right? I didn't look this up. I suspect the average US height is taller than the average world population, but I'm not sure. So I didn't look this up. So to form a null hypothesis, I'm not done yet. I need a specific probability distribution. What's a good option here? Yeah.
The mean and square root of 5 as the variance.
Or the square of
Square, yeah.
So pretty close, yes. So great. So I'm going to have my null distribution as a normal distribution with 67 inches as the mean, and the variance will be the square of the standard deviation. That'll be 25 inches squared, right? So this was the inches. This is the mean, and then so this will be the variance, right? So this will be in inches squared. Yeah, okay. So if I just have the mean and the variance and it's a continuous random variable, I'm probably going to use a normal distribution, okay? That's kind of a pretty good, default. Is that a good choice here? It's probably going to work okay. If I look at the actual heights, in these states, you'll see it doesn't actually look like a normal distribution. The actual heights will truly look there'll be something like 70 and 63. And there'll be kind of these two bumps sort of like this. It's not going to look like a normal distribution. It turns out that, if you're, there are two bumps typically because if your sex is male, you're typically taller than if your sex is female. Based on birth. And so these, it's not exactly going to look like a normal, but for the point of this exercise, we're going to kind of ignore this. Okay, we'll use a normal distribution. It'll make the calculation simple. Okay, if I were trying to do this, I might just look at just the male, or just like the biologically male or biologically female as the test, and do those separately. Or I could try and have a more complicated distribution with more parameters I'd have to try and tune. So okay, great. So but I'm gonna, to start out to simplify, we're gonna start as this is gonna be our null distribution. Okay, so what is now I need to formulate my alternative H1 distribution. So what is the H1 distribution going to be? That Utah is taller than average. How do I translate that into mathematics here? This one doesn't need to be a full distribution, but I want to write it up mathematically. Yeah. Yeah, right. So we'll say that the mean in so Utah is going to be greater than 67. Okay. So I don't need to say specifically what the distribution is. Kind of implicitly, I'm assuming it's still a normal, but that doesn't really come too much into play. But I'm assuming that the mean of the Utah, the expected value of the Utah distribution is larger than 67. Okay, so this is an example of forming a hypothesis. It's important to state when you do this that you're assuming normality, if I'm doing so, which maybe is not the right thing to do here, but this will still be kind of an example that so we can work through it. Okay. All right, and we're specifying this as the, as an example sort of hypothesis. So, okay, so now this was, step one, right? Remember, step one was to form the hypothesis, right? And so this is what I mean by that. You need to specify the null distribution and specify the H1 distribution. Again, typically you're going to take one parameter of that distribution and say, I think that parameter for the data I'm going to collect is going to be larger than that for the null, or maybe it's smaller, or maybe it's kind of it's like different. You could say it might be larger or it might be smaller. I'm not sure, but it's not the same, right? So that's less useful. Usually do one-sided sort of tests here. We'll maybe, I think tomorrow I have an example plan that shows a two-sided test. Okay, but typically with confidence intervals, we usually did a one-sided, two-sided kind of bounds. We're going to do a one-sided, typically you do one-sided hypothesis tests. And so it'll look similar to confidence intervals, but there'll be some change in how we kind of look up these, these values in tables, because we only are going to just look up one side. Okay, so step two is going to be to design the experiment. Okay, so to design the experiment, I'm almost always going to start with a random sample, x1, x2, up to xn. All right, so let's pause and think. If we're going back to this example with the height, right, with the height in Utah. So how would I collect a random sample? So is there a good way to get a random sample? Yeah, great. So I could go around to different buildings on campus and ask people if I can, if I can measure them, see like how tall they are. This would be like what's called like a convenience sample. You kind of picked a sample from the right population, but not a real attempt to like, you picked it so conveniently, but not necessarily is going to be a good example of like a random sample that's a good, distribution. So for instance, let's say we picked a sample of people from this class. Okay, all of you are probably computer science, electrical, computer engineering, or data science majors, or like software development, majors, or what's it called? Software development majors. So the thing about that population is what we know by looking at the data at the university is that it's majority male. I know the computer science degree is 85% male. The data science degree is so 80% male. I don't know what it is in the electrical computer engineering degree, but I'm guessing it's in that space, you know, so someplace. And we thought about earlier that like there's actually a bimodal distribution. And so if we're sampling more from the mode that has larger heights, then it's not going to be a very representative sample, right? So sampling from this classroom would not be a great way of doing this problem. Yeah, so what would be another way of getting maybe a sample that might be more representative?
So we could choose multiple locations across Utah and then do that same sampling.
So we would do the convenient sample where we go ask people, you know, to measure their height, but we didn't just do it here, you know, in this part of campus or by the engineering building, but we did it in various spots around Utah. Yeah, so if we picked enough spots around Utah, this would probably be random. Yeah, so this could work. It seems typically in this, you know, sort of situation, you would probably rely on existing measurements of people's heights. You could remeasure people, like I know for like the NBA draft, they have like the combine and they actually measure them, and it's always a little bit different than what they reported. But let's say we got heights, you know, like from the doctors, right? So like from the medical records, right? So actually in the state of Utah, there's something called the Utah Population Database, which only exists in the state of Utah because of some decree of the governor like 50 years ago. But it's a database that collects all the heights, basically all the medical records of people who are like living in Utah. And so we could actually take a full random sample. So from this, of people who we think are of like the college age, for instance, or are above a certain age when we think they've stopped growing. And they have like the medical records, which often may include the height information, right? So this would probably be a pretty good sample of the state of Utah. So this would actually be an option here. And this is probably similar to actually how they create sort of statistics for this. They have a bunch of medical records, and they probably keep an aggregate average across some various states in some similar ways like this. So, okay, so we need to create the random sample, but it's not always as easy as it seems. If you're dealing like analyzing randomized algorithms or something, you can actually generate random samples fairly exactly, or scientific experiments, but population experiments are so kind of tricky sometimes, actually, to get this right. Okay, so we're going to start with the random sample, and then we're going to kind of, we would like to kind of create a test statistic. Okay, so once we've resolved how we're going to create the random sample, we're going to create a test statistic. Okay, and this is some value t, which is some algorithm that we run on x1 through xn, our sample. And in this case, we're interested in the average, right? So we're going to probably call this, in particular, we're going to do 1 over n, I equals 1 up to n xi, right? We're going to create this kind of the sample average. It would seem a pretty useful test statistic in this case. Yes. These are all capital X's. Yeah, these are still the random variables. Step 2, we have not collected the data yet. We're designing the experiment. We need to talk about the random variables. Great. So thanks. So a good question. Again, these are random variables. So, okay, we're going to create this test statistic. Okay, and kind of intuitively, we think I'm going to, if I sample data that I believe is random, and I calculate an average height from my sample, and if it's larger than 67 inches, I'd say, the Utah population might be so taller than the average, which would be, say, 67 inches. Okay? Right, okay, so But how large does it need to be for me to say, yeah, that's large, I'm actually convinced, right? So that's what we need to kind of do it in this design, okay? So we'd like to say, so what I'm gonna pick a, so confidence level, so alpha, okay, and a common alpha would be 0.05. And so this would lead to like a 95% confidence, or 1 minus alpha, the confidence level, 1 minus alpha. So if I'm, so I would like to get like a 95% confidence is a typical value you would consider. And we're gonna describe what we call a, so critical value at, so alpha, okay? A critical value at alpha is gonna be a value where I could say, well, if I actually recorded data and the data is bigger than this threshold, then I'm actually going to believe with 95% so confidence that the population of Utah is taller than 6-7 inches on average. Okay, so this is a value we're going to call T alpha. Okay, and this will have the property that the probability that my test statistic is less than or equal to T alpha is equal to 1 minus alpha, assuming that T is right where that x1 through xn is from the, so is going to be from the null distribution. Okay, and then T, and then I'm going to use these to create the random variable T. Okay, so T will be the random variable describing the test statistic, and then I'm going to create a critical value, right? The critical value at alpha is such that if this data was drawn from the null distribution, and I turned it into this test statistic T, that the probability that the test statistic T was less than this critical value is 1 minus alpha. So the probability it's greater would be alpha. So if we chose alpha at 0.05, that would mean the probability that T was greater than T alpha would be 5%. Okay, so this is, we want to come up with this threshold. So then when we go gather our data, we can compare to that threshold and we can decide, I'm 95%, so confident that the data that based on the data that the population of Utah is larger than the average population in the in the United States, assuming it was followed the normal distribution. Okay, so kind of I wanted to say a simple sense there that I believe with probability at least at most at most, so I'm based on the data I found, at least 95% of the time, if the data was from the normal distribution and it was a random sample from the state of Utah, it would not have been this small, or it would not have been this large. I kind of need to condition the statement in a careful way to say this. I need to say, well, I assume the data was from the null distribution. I need to say that the probability it could have occurred was 95%. That was alpha, the parameter I chose. Right? You need to kind of put all this together into these statements. Okay. So now how do we calculate this value T alpha, right? Conceptually, this makes sense, right? This is a threshold. If we gathered data and it was larger than this threshold, we would probably be convinced that the population in Utah was so tall or taller than the null distribution. How would we create this value T alpha? Okay, yeah, so it seems, so what we're going to do is we're going to do something like a confidence interval. Okay, but we're only looking at one side. And so we're going to, so if we assume that each xi is from the null distribution, or which I'll say as mu, so sigma squared, then we'll be able to say xn bar is going to be from the normal distribution, which is mu sigma squared over n, right? Remember, the variance goes down at a rate of 1 over n. So if we're averaging over n things, we now have an understanding of the distribution of xn bar, okay? And so then we can say, well, well, this is a normal distribution, so I want to make this into a kind of a standard normal instead. So I'm going to say Zn is going to be equal to xn bar minus mu divided by sigma over square root of n. This is now from a standard normal distribution, right? I've subtracted off the mean, so now the mean of xn bar is going to be 0, assuming that xn bar came from this normal distribution. And I've divided through by the standard deviation. When I do that, the standard deviation of Zn bar is going to be exactly 1. So it's a standard normal distribution. Okay, so now if I look at Zn bar, I can look this up so I want the probability that Zn bar, now I can do the probability that Zn or Zn is less than lowercase z alpha equals 1 minus alpha. Well, this is exactly the same z values that we look up in a table, right? This is the cumulative density function for the normal distribution. And this is something we can look up in a table, right? For instance, this may be 1.96, for instance, right? So if that was 5%, that I get that the alpha equals 0.05 when z alpha is 1.96. But now I want to compare this to my test statistic, which was just the sample mean, because I didn't know, or I knew mu and sigma. So I could make Zn my test statistic and then use this as the threshold, but I want to, so translate this back, right? So how we do that is that we can set now to T alpha, my threshold is going to be mu plus Z alpha, that's the 1.96, times sigma over, so square root n. Okay, so this is how I get this critical value at, alpha. If I'm assuming it's from a normal distribution with a known mean and known variance, that was my null distribution. Okay. Once I have this, okay, I know the values I'm given on the input. Remember, my H0 was, in general, was this mu, so sigma squared. So I got on input mu here and sigma squared, which gives me this one. And then I can decide how many samples, the number of samples I'm going to collect, right? This n is this value n here. And also finally the Z alpha, I can look up in a table based on this standard normal distribution. Okay, so I can set the T alpha critical value based on all these things I'm either given, which are in pink, That's from my null hypothesis. I can look up in a table that's in the orange, or I can design my experiment. That's the number of samples. That's in the blue. Okay, so I can calculate this critical value, and this is how I am designing my experiment. Yes, okay, great. So then if I went and collected heights from people like from the Utah population database, I calculate the average, I compare it to T alpha, and this is yeah, so that's how I'm going to design the experiment. Yeah. Yeah, okay, so I could, right, so this is an interesting question. So how should you choose n here, right? So I haven't said how to choose n, and I get a valid critical value for any choice of n, right? So how do I choose n? Oh, well, okay, so yeah, so let's say that I have mu here, and I actually say my guess of, say, mu 0 of mu 1 is like actually over here. Okay, so I'm going to kind of say I kind of know where I think the height is, right? Maybe this is 67 inches, and this is 67.5 inches. Okay. So if I have it so that, and then what I'm going to do is I'm going to collect a bunch of data, and I'm going to compute some sample average xn bar. I think it'll look somewhere around there, right? And I can only kind of, the only way I can design my experiment is by comparing it to T alpha. So let's say I calculated my T alpha, which is mu 0 plus kind of Z alpha, which is a fixed quantity. I can't change this, right? Times sigma, if I knew that, divided by n. So what I kind of have as my, remember, in my assumption, these were assumed. This was something I looked up in a table, and n is something I can design in my experiment. Okay, so if I chose n so that T alpha is there, is this gonna probably be a good experiment? Well, it's an okay experiment, but I don't expect the xn bar. I want to know, I'm gonna check, the probability I have the xn bar is greater than T alpha equals 1 minus alpha. And what I'm going to do in step 3, I'm going to check. I'm going to compute xn, the realization of xn bar, compare it to the value T alpha. But right now, my expected value, this is my maybe expected value of xn bar here, which is less than T alpha, yet there's still a gap here, right, of 0.5 inches. Okay, so the xn bar is larger, but I set my T alpha value so that, well, it's too big. What could I do to change that? What would happen if I use, maybe this was for n equals, this is the value for n equals to 1, right? Let's say I took one sample, right? I took one person at random, and that's all I can afford with so from the NIH, I said, we'll give you money to measure one person, right? I was like, okay, well, if I only measure one person, then my T alpha value is going to be way out there. I would need Utah population to be 1 inch taller instead of half an inch taller than average. Well, so say, then you want to go back to NIH and say, I want more money to measure more people. Because what's going to happen if I measure more people? What's going to happen to the T alpha value? I'm taking, if I look at this, I'm taking mu 0, which is here, and I'm adding on this term, right? So this distance here this is Z alpha sigma over square root n. Two of those things I can't change. I can't change Z alpha unless I give up on my confidence. I give lower confidence. And I can't change sigma. I assume I knew what sigma was. But I can't change n. If I change n, this value here, this value gets smaller, or square root n gets larger. So that means that that term, Z alpha sigma over square root n, gets smaller. Right? So now I go back and I say, well, you know, if I measured 16 people instead, n equals 16, then I'm going to have basically my T alpha is going to be over here. Okay, and that's going to be interesting. Now, if Utah really is half an inch taller than the national average, I'll be able to see it now. My T alpha is going to be at 0.25 inches bigger than the national average. Okay, so if I increase the number of samples, I get a better concentration on my estimate, right? Our variance goes down on the estimate, xn bar, right? So I'm going to be able to have a smaller threshold if I increase the value of it. Right, so this kind of helps me choose. So I can run an experiment with one sample, but I do better if I have more samples, right? And as n increases from 1 to 16, that square root n changes from 1 to 4. So the distance I'm moving from mu0 is being cut to 1/4 of what it used to be. Okay, so I can get I can more easily determine if I have kind of crossed the critical kind of A, that if it is taller with more people, because I have a more refined measurement on that my estimator is better. Okay, has lower variance. So it's, yeah. Yeah, so alpha, you say, how confident do I want to be? Maybe if this was going to go into like there's some therapy people could take because they're too tall. And so I want to be confident that Utah is actually taller than average, right? Because of airplane seats and such. So I want to, but I want to be 99% accuracy, and 99% confident, or 99.9% confident, because so then I could change alpha, right? So it depends on how confident you want to be in in the test, right? And so how confident you want to be is the choice of alpha, right? And how and n decides how specific is your experiment. All right. Okay. Okay. Let's try and finish this up. There's I don't think we're going to get through quite everything I want to today, but we're going to finish up the core hypothesis testing, and then I'll talk about. I'll try and draw some other pictures of what's going on and other examples on Thursday along with the R. So that's fine. So okay. So the last step 3 is to actually run the experiment. Okay. And so I'm going to introduce some important language and terminology at this point. Okay. So at this point, I'm going to have realization of the random variables. We get x1, x2 up to xn, and these are now lowercase. Okay, so these are actual data I've collected, right? I'm going to then create the true observation, the test, so the realization of the test, so statistic, realization of the test, of the test statistic, and I'm going to run through my algorithm T, but now I'm going to put in actual values on the input. I'm not just analyzing my algorithm. I'm actually, finally, I get to run the algorithm, which is just taking an average, right? So this is going to be xn bar with lowercase x, which is 1 over n. It's 1 to n xi. Okay, so I'm actually taking the average of all the observations. Okay, and then there are two options. Okay, if this value t, right, if the value t is greater than t alpha, right? So I put all this work in designing to get the value t alpha. It's not that hard to get it, but if t is greater than t alpha, okay, well then I'm like, okay, I'm excited. What you say now is that you reject the null hypothesis. Okay, so this is the terminology to use. Okay, to reject the null hypothesis, you'd say there is sufficient evidence. That means evidence that you believe with 1 minus alpha %, confidence. So there's evidence that you believe with 1 minus alpha %, confidence. So that that the alternative hypothesis is more likely than the null hypothesis. Okay, so basically I want to reject the null hypothesis. It doesn't mean the null hypothesis is definitely not true, but it means that, well, with 1 minus alpha %, confidence, or 95%, confidence, right? That I believe the data says alternative hypothesis is more likely than the null hypothesis, or some alternative hypothesis. Remember, because we didn't fully specify it, but some alternative hypothesis is more likely than the null hypothesis. Okay. Okay. The other option is if t is less than or equal to t alpha, right? This can also happen. Remember, if we chose one person to sample, then this was what we thought was likely to was probably going to happen. Okay. Then we would say that we do not reject the null hypothesis. All right. In this case, I'm not saying the null hypothesis is correct. I'm not saying it's wrong. I'm just saying we do not have sufficient evidence to reject the null hypothesis. Okay, so if I only measured one person, it's unlikely I'm going to have enough data, enough evidence that I actually believe that we would, reject the null hypothesis. Maybe if I measured one person and they were like 8,000 feet tall, then I would actually believe it. But even then, that's probably an outlier, right? There's probably something else going on. So okay, so this again, this does not confirm the null hypothesis, right? You should not claim something like, okay, I ran my hypothesis test and I determined that t was less than t alpha, so the null hypothesis is true, that Utah is the same average height as the rest of the US, right? I've not done that. Okay, and so this is kind of kind of a somewhat common mistake to make. So you don't want to say you confirm the null hypothesis. You say you do not reject it. It's like a double negative, and it should be a double negative, not reject. Confirm that was the same. Yeah, so hypothesis testing is not designed to do that. It's not designed to confirm that two things are the same. It's to, you might be able to, with some confidence, reject that they are the same, meaning you believe that they are different. You could say, what you would want to do is if you set up the T alpha value to be, you could set up a value. So this is my null distribution, and so then I could put instead, I can say so if this is the null, so like the null distribution, I can then put in some x bar n, right? This is from my random sample, x bar n, and this is ln, so Rn, right? So what is this looking like? This is looking like a confidence interval. I can say that the probability that ln is less than xn bar is less than Rn bar is equal to 1 minus alpha. So I could say 95% of the time, xn bar is within this range around kind of, what I believe is my null hypothesis. And if you look at this, I kind of drew it intentionally small. You could imagine like my T alpha, T alpha, you might say, to reject the null hypothesis might be all the way out there. Okay, the T alpha might be all the way out there, but the confidence interval, I'd say there's, it's unlikely if something fell out there, then I would reject it. But if it's in the confidence interval, I say, well, I don't know if it's, if it's exactly the same, but I can say with 95% confident, it's going to be close. So a confidence interval allows you to say that. It doesn't allow you to say, oh, they're exactly the same. This is probably not exactly the same. But so you have to define a notion of close in order to do that, and you say it's probably close. And that's what the confidence intervals are so giving you instead. Okay. Maybe I'll say what a p-value is, and we're definitely going to review this. So a p-value, okay, is something you sometimes compute. So it's the so I calculate the realization of the test statistic, and I'm going to call this T, and then I want to determine the probability that this is the random variable test statistic from the null distribution, and I want to set the probability of this equal to 1 minus p. Okay, and now I need to, this is 1 minus p. This p-value, I need to then say solve for the value p. Okay, so I can write down this. So t is a random, uppercase t is a random variable. Lowercase t is from the observation of the data. So this is from the data. And I have an uppercase T, which is from my null distribution. And if I say, well, what is the cumulative density, the CDF of the random variable from the null distribution at the value I actually observed? 1 minus that is the p-value. Okay, and I just want to wrap a bow on this part of the lecture. We will revisit this on Thursday, and I will draw a picture and trying to help you put these things in context. But this is this is what the p-value is. Okay, so we'll come back to this and review it. I know this was a lot, but we have enough time this semester to spend as much time on as we need on this topic.